All right, so welcome back. Welcome back to this YouTube channel. So in the last video, we have looked at autoencoders. What are autoencoders? That like we looked at the basic introduction to autoencoders. In this video, we are going to do something similar. We are just going to elaborate on that idea a little bit further. We are going to take this further, like one step. So we are going to first look at some applications of autoencoders. Like probably by now, after understanding like the architecture of autoencoders, you might have a very huge confusion on like when we'll actually use these models. So I have actually solved one problem for you. Like I have given one solution that we'll use this for image generation because this video is under the image generation section, right? So that is one thing, and I have also like put a problem before you. I have put a problem before you on how we can actually generate new images that are similar to each other. I will I'll pause the solution. I'll keep this solution as a suspense for one more video. In the next video, I'll probably start variational autoencoders. So in this video, as you have seen in this title and probably the thumbnail, we are going to first discuss some of the applications of autoencoders, and also we are going to develop an autoencoder from scratch in TensorFlow. So yeah, stay with me till the end, and let's get started. So I'm going to share three applications, and we're going to build all of these three. No, we're going to build two because the other one requires variation autoencoders. You have to understand variation autoencoders to actually build the other one. So first we'll understand. I'll probably try to elaborate three applications, and then we'll develop two of them. We'll build them from scratch right now. So I'll try to cover them as fast as possible. So let's get started. So the first application that I want to share with you that we'll be doing is called denoising. I'm going to I'll tell you what that is in just a minute. So essentially what you do is you'll just take a image plus noise and just get this image. So essentially you will take this image and pass that through autoencoder and get this image, and make sure that this image does not contain the noise, right? And then the other problem that we're going to solve is called, I think, yeah, anomaly detection. We're also going to build this now. So essentially what is the idea is, I'm going to share the idea in like I'm going to share what the idea is. For example, let's say there is some data. For example, in this project, we are going to take a ECG data. What is ECG? What is ECG? I'm going to search. I'm going to take like ECG data. Yeah. Electrocardiography, like records of the heart. For example, like there is heartbeat, right? I think it is somewhat connected to heartbeat. Like I'm not that good at biology, but I think it is probably the rate of heartbeats, maybe over time. I have no idea, but I don't want to talk about it. So there is going to be like some graph. So it is going to be some time series data, right? I mean, if you go to hospitals, I recently went to the hospital. Yeah. So there is going to be a graph, right, in which there is going to be like this data, right? Something like that. Not pretty accurate. So what we'll be doing in this project is we are going to take in this series. Essentially, what we are going to do is we are going to taking some real ECG data, and then we'll train the model. We'll train the autoencoder on this data, such that the autoencoder is actually trained to actually predict this type of data, right? It could actually predict this type of data. So that is the idea. And but what if we put in the same architecture? What if we use the same architecture but on fake data? So this is fake data, right? This looks like fake data. For example, you have data like this all around your training data set. You train the model on real data, and then you test it on fake data to see if this data is real or not. So if the autoencoder predicts on this data with a very high accuracy, if autoencoder is actually able to replicate this output, if it is able to replicate it, right, that is the job of autoencoders, right, to actually take in this data and replicate it. I mean, the autoencoder can replicate real data because it is trained on real data, and because it has not trained on fake data, it can easily catch fake data because it is only trained on real data. So for example, if given a like data like this, given data like this, the autoencoder might predict something like this, right? And because there is a lot of difference between the fake and the autoencoders generated, we're going to predict that this data is actually fake. So that is how we could do anomaly detection. Anomaly stands for fake or real. So we are essentially going to train the autoencoder model on real data to actually make it to implement or create that real data. Yes, that is the idea. And the third application you could do that we'll be doing in the next few videos is actually using variational encoder autoencoders to actually doing image generation, right? Generating new images. So that is another application that we'll try to cover in the future videos. One of the future videos, maybe the next one um, or the next one. I'll see. So I'll try to I'll just give a quick summary of autoencoder architecture. What autoencoder actually is. So the idea of autoencoder is actually taking an image and trying to reconstruct this image, right? Just trying to reconstruct this image. So for that, we'll just pass this model to like a CNN, and we could actually get this CNN, which is like the lowest output, and we actually this will be like feature representation of this image, and we could actually use that for training, right? I have said that. Then we could actually reconstruct this image. For the loss function, we're going to perform an MSC, taking this and this. So we're going to take this and perform an MSC. So we're going to perform bunch of, and this is like the lowest point or the lowest feature vector that we can actually use to represent the images. And as I have shared before, while training stable diffusion, also we're going to use this technique to actually like slow the training process. Sorry, or like reduce the complexity of training, reduce the computational requirements of little training, right? You have lesser images, then lesser computational power is needed, right? To actually perform all of the things that we do in stable diffusion. I'll probably try to cover stable diffusion also in this series. Okay, all right. Anyway, so this is the idea of autoencoders, right? We're going to have encoder, which is like compressing this input into like this feature representation. So this is the encoder, right? And then we're going to have the decoder, which is going to take this feature representation and rebuild it to be same image. And essentially, the only thing we are controlling, like the loss function, is going to be MSC between the actual image and real image. So all of these layers will try. So these layers will actually try to encode this image into this such that these features are actually folded in this feature representation. So therefore, the goal of the encoder is actually make sure the feature representation contains all of the features, all of the important features that are contained in this actual image. And the goal of the decoder is to taking this feature representation and actually reconstruct these features. And all of these layers are going to be updated by this loss function. The loss function is like not all of these layers. Of course, we are going to have do the chain rule, right? We're going to calculate the derivative with respect to each other, with respect to the following layer, right? So we're going to take the loss function and we're going to gradually update like to back propagation to update all of this way. So that is the idea. So pretty simple, right? So we're going to compress, we're going to have encoder and decoder, and like we're going to reconstruct this image, right? So like these are some applications. I've shared some. I have shared some applications with you. So we'll be trying to. I actually have a notebook here. We'll be trying to go through that. I'll like connect my mouse, because while using whiteboard, I of course need my drawing board. But now let's go through the code. I have built this notebook for us to actually go through like everything, right? All of the we're going to build like two applications. And first we're going to build like a normal autoencoder for like normal data. So the data set that we are going to use in this notebook is going to be fashion MNIST data set. If you don't know, fashion MNIST data set is a data set in which there is like clothing images of like 10 classes. So there are going to be 10 classes or 10 types of clothings. I think, yeah, I think they are like, I don't know, like these dresses, shirt, pant, and shoes and all that. All right. First, we'll import the necessary libraries, right? We'll be needing matplotlib. We'll be needing matplotlib to actually plot these images. All right. And we're going to need NumPy for, of course, like conversion and all that. While training, we have to convert our data, like images, into like NumPy arrays, right? To actually train them. Right. And then we're going to use pandas for like data frame. I think, these are like libraries that you should like import in like every deep learning project. Like when I was learning machine learning, I think like 3 years back, I took a course, right? In that course, like this is like the main default code. So no matter what deep learning project you are building, they ask me to actually write this like 4 lines and by heart it, and it's like you know unconscious. I'll just unconsciously write this 4 lines. So yeah, that's good. So these are some main libraries that we'll use in like almost all machine learning projects. Anyway, we're going to use scikit-learn metrics of accuracy, score, precision, and recall. Precision, recall is actually some other evaluation functions. I think I'll talk about them in the future maybe. Yeah, well, I think there's formula. I'll probably go through the formula. Yeah. Yeah, so this is it. True positives by true positives plus false positives. True positives being like positive means like belonging to the positive class, and then true means like the outputs and the inputs are positive, or yeah, plus, and then true positives plus false positives being like total number of correct answers predicted by the model. So that is the how you can calculate the precision. So yeah, number of true positives by true positives plus false positives. So sorry, false positives is like the actual like the actual label is positive and the model predicted it to be negative. So that is false positive. And we could actually increase this formula to actually have the number of classes we have, right? We could actually do that for like all the number of classes. That is precision. And recall is, I think, something similar. Let's see. Yeah, so this is recall. Yeah, so it is like true positives by false positives plus false negatives. So like I think there is some like there is like some like detailed statistics, like why you use this recall and precision. I'll probably cover that in maybe in future video. So just don't worry about them. They're just like evaluation metrics to actually evaluate how good our model is. And of course, we are also going to import accuracy to actually see how accurate our model is. And then we're going to import train test split to split our data into train and testing sets. I don't think we actually need that, but let's see. And then we're also going to be importing layers and layer losses. We are going to import fashion image data set and also model function to actually create models, right? TensorFlow models. Build like TensorFlow layers and combine them to actually build the TensorFlow model. All right. So if you can see the shape of this X train, so X train is going to have like so each image is going to have like 28 by 28, 28 by 28 numbers. Like, and we're also going to deal with only white black images. So that is why we are not going to have like 3 channels, like 28 by 28 images. And like we're going to have 60,000 training images and 10,000 testing images. So yeah, that is a lot of number of like huge number of images. So first, let's build our autoencoder, like basic autoencoder. We are not going to perform any like denoising and all that. There's going to be like a basic autoencoder that just takes in an input and try to reconstruct it as the output. We're going to see a look at how to build that. Not like complicated science. If you are a student of deep learning, you should be able to do that too. So first, we'll set the latent dimension, which to be 64. Right. So I don't think we'll be needing the latent dimension. I'll probably remove that. So and then yeah. So yeah, latent dimension is actually the size of this like smallest box. So latent dimension is the size of this feature vector. I'll probably name this to be something else. I don't know why I've used this name, but you know, probably feature representation would be a very good word. But let's see. Latent dimension is 64, and then we are going to build the autoencoder class that inherits from the object model. Um, and then we're going to create an init function, initialization function that takes in self and latent dimension, right? And then we're going to inherit from autoencoder and all that. Now let's like specify the latent dimension. We'll just create a self object or self variable that we could use in this class. So self dot latent dimension equal latent dimension. Right now, let's build our encoder, which is nothing but self dot encoder is equal to, we're going to build a sequential model. We're going to call the sequential function method. We're going to call the sequential method of the TensorFlow keras class, and we're going to import two layers, right? So we're going to have two layers. Essentially, we're just going to take in the image, right? Flatten these outputs, flatten the image, and just perform one dense layer. Yeah, you're not even two dense layers, just one dense layer. Just like one layer encoder and one layer decoder. So that is like, yeah, pretty basic, because we are not actually solving a huge problem, right? Like, you could definitely increase the number of layers. You could use like different architectures, maybe residual networks and all that. Yeah, that's for you to like experiment. And then we're going to have this dense layer as the output, and the activation is going to be ReLU. And because we are not working with convolutional 2D layers, we are not working with convolutional layers, we don't have to use like convolutional transpose or something. We could just say the number of neurons, because in dense layer, the number of neurons is going to be the number of like the size of the output. So therefore, it's actually pretty simple. We could use the same dense layer, but with like different values. Again, I think 28 by 28 into 28 is 784. Yeah, 784. So as you can see here, we're going to build the decoder, which is going to taking this input. We're going to take this feature representation and apply a dense layer of 784. Right, we don't have like 784 neurons, and because we're just going to get a vector, output vector of 784 neurons, or 784 outputs, because 28 into 28 is 784 pixels. We're going to apply sigmoid for activation functions, because white or black, right? And then we're going to reshape this input. So the output of this layer is essentially going to be like a vector, a one-dimensional vector. So we are going to reshape this output into a like 28 by 28 image or matrix to actually make it an image. And then we'll build the call function, the main call function, in which we'll take an X, which is the input image. We're going to pass that through the encoder, and then we're going to pass the output of the encoder to the decoder, and we're going to return the decoder. It's pretty simple, right? And then we could actually create the object of encoder with the latent dimension, which is here 64. I'm going to run that, and let's compile the model with Adam optimizer and mean squared error as loss, because yeah. Now let's train our model. If you look at the training function, we're going to pass in xtrain and xtrain. So remember, while training a TensorFlow model, you will just say model.fit on x and y. So this is going to be the input and this is going to be the output. But in this case, as we are training an autoencoder, we just want the model to actually replicate that image or reconstruct that image. So therefore, the input is going to be x and the output is going to be x. So essentially, for each image, we're going to have like the same image as the output. So yeah, because autoencoders, right? We're going to reconstruct these inputs, and we're going to run for 10 epochs, and we're going to shuffle these values. We are not going to shuffle x and y separately, because that will ruin the like values, of course. Like, pretty dumb, right? So we are going to shuffle these pairs and all, because we don't want like same classes to be nearer to each other. That may cause the training to actually be more suited to the last examples sometimes. And then we're going to use the validation data. We're going to set validation to data to xtest and xtest. So again, here input is going to be x and output is also going to be x. Because we are just reconstructing the outputs, right? Now I'm going to run this. It may take some time, and I don't think it'll take a lot of time, because even the model is pretty small. Let's see. Yeah, it is pretty fast, right? Like, compared to this model. So just make sure that you are using a GPU. I mean, because just because it is free, right? When you're training a model, you can just use a free GPU. And when you are training like huge models, because that is the only reason why I am not able to train my like own language model and all that in the video. I'll probably try to buy the subscription. It is training. All right, 7 epochs, and we're down to like 0.009, which is actually pretty good. Pretty good. 0.089. Yeah, pretty good. Yeah, good. Right. We have attained like pretty good accuracy, I could say. Sorry, loss, like pretty less loss. So yeah, it is going to just save the model and all that. Mhm. 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 All right, done. Now what we'll do is we'll just taking the X test images, the testing X images, the texting images, and we're going to convert them into NumPy arrays, and we're going to pass them through the encoder. We're going to pass them to the encoder, and we're going to pass the output of the encoder to this decoder. Essentially, we're just taking each image, and we're going to predict a probability or predict a or do a prediction for this input image being the actual input image. So just replicating this input image. And now let's look at this function, what we are doing here. I'm going to say n is equal to 10, and we're going to set some figure size. I'm going to loop through n. I'm going to say for I in range n. So we're going to loop like 10 times. And then what we're going to do is we're just going to show that image x test I, right? And then we're going to like perform the like, yeah. And then we're going to like okay, set a title called original. So this is going to be the original data set, right? On the xtest data set, xtest is like the original data sets from the fast nameless data set. And then I'm going to set the plt dot gray because the images are black and white, right? And then I'm going to display reconstruction, I'm going to select the like plots and all that. And I'm going to I'm going to say plt.im show to actually show the image. And I'm going to say decoded image, which is the NumPy array that we have created here, right? We have performed the encoder and decoder, right? On all the X test images. And we're going to call this decoded image. So the exact I index at decoded images. And we're going to set the title to actually be reconstructed. And we could actually show this plot. So this is the plot. So these are the original images, and these are the corresponding reconstructed images. So these are essentially the first 10 images of this test set, and these are the predictions or reconstructed images. And to be honest, like but it kind of looks similar because keep in mind that we have only trained for like 10 epochs, and this is like pretty good performance. And even the problem is not that hard. So therefore, 10 epochs does have done the job. And we have remember we have only set like one layer in encoder and one layer in decoder. So yeah, good performance. Now let's we don't have to run this again because we have already imported extend next test above. So again, no need of that. Here what I'm going to do is now let's get to denoising. So we have finished like one part, the first part, which is actually reconstructing the original images. Now what we are going to do is, there's no need. So what we are going to do here is we are just going to create noise. So we are just essentially going to create noise and just add noise, right? Just to make it a little harder for the model. And we're going to taking this noise, right? And then we're going to make them autoencoder predict the actual image, right? I'm going to see, right? The model will taking the extra noisy image and try to predict the actual image. So that is the idea of denoising, right? As you can see here, I'm going to set a noise factor, which if you increase, the more noise will be added, right? The lesser noise, and the higher the noise factor, and then the higher will be the loss, sorry, the noise. So I'm going to create new variables or new data, extrain noisy and extest noisy. So in the extrain noisy, I'm going to say extrain images. So I'm going to take in each image. So that is actually the advantage of using NumPy. When you're actually using NumPy arrays, you could actually add them just like that. You can just add scalars or even add like NumPy vectors, right? So that is idea. So what I'm going to do is I'm going to say, I'm going to take in the extrain. I'm going to add that to this term. This term here means like, so tf dot random dot normal is actually going to create as a Gaussian distribution, random Gaussian distribution, in which the shape is going to be extend dot shape, because to actually add two matrices, they should be of the same shape, right? I'm going to create this random like random vector matrix. I'm going to multiply that by noise factor. I'm going to add that to the extend. So that is, I'm going to do the same for x test 2, the testing data set. I'm going to take in x test. I'm going to add that to noise factor multiplied by this this distribution, whereas the shape is going to be x test dot shape, right? I'm going to, what is clip value? Yeah, so I'm going to do that, right? I've actually forgot that. Like there are some many like TensorFlow values. You don't actually remember all of them. Mm, yeah, something like that, right? So yeah, we are going to set the like minimum values to something and maximum values to something. So if you can see, the most minimum value will be set to 0 and the maximum value will be 1. So we're essentially creating like a, like a thresholds. So make sure that the values are between the range of 0 and 1. So that is out of clip by value, you know. And then now let's just plot these measures. I'm going to set n equal 10, and I'm just doing the same exact thing that we have done above. So we're going to set the figure size and we're going to loop through n. So we're going to loop 10 times, and then we're going to just show these images, right? We're just going to show these images, and as you can see here, the images are pretty blurry. If you see here, they are like too super smooth compared relative to these images. These images are like pretty noisy, and even I couldn't actually like detect some images. Maybe if you look at the whole data set, for example, this one is actually pretty hard to find comparatively, and even this one too. So yeah, as you can see, we have this noise. So the goal of our model is actually taking this image and predict the actual image, right? I'm going to create a class denoise in which I'm going to build this model again. Here now I'm going to use like con2d and con2d transpose, because of course the problem is a little more complex. I'm going to, yeah, because of course we want a better model to do this, because like it could be pretty hard, right? There are some like hard features to find. So what I'm going to do is I'm going to like create a class called denoise that is going to inherit from model, and I'm going to create a variable self.encoder, which is going to be sequential. Like I'm going to call the sequential method from TensorFlow. The input shape is going to be 28 by 28 by 1. I'm going to use a convolutional 2D layer, 16 kernels, 3 by 3 kernel size, activation, ReLU activation function. I'm going to use padding and strides. I'm going to use again another convolutional layer with 8 kernels, and each kernel being 3 by 3 shape of shape 3 by 3. I'm going to set the activation to be ReLU and padding equals same. I'll also build the decoder, which is going to be taken, which is going to be in which we are going to have like this is going to be the first layer. So again, remember, this is like the feature representation after performing the combination layer. So this output is going to be the feature representation, like yeah, the latent vector in like the previous words. So I'm going to perform a convolution 2D transpose now, right, with 8 kernels and kernel size equal 3 and stride equal 2. I'm going to perform other convolution 2D transpose with 16 kernels now, because the size increases, right? And then finally, I'm going to perform a one dimensional, like one. I'm going to perform a simple convolutional 2D layer as the output. I'm going to have like one kernel with like 3 by 3, and I'm going to use a sigmoid activation function, because of course white and black images, and we have also clipped the values between 0 and 1. So yeah, that does make sense, right? I'm going to create a call function in which I am going to take this input image, pass that to the encoder, and get this output of the encoder and pass that to the decoder and just return the decoded image. Right? I'll just create the object. I'll create the object autoencoder. I'm going to call this function. I run this, right? And now I'll actually compile the model with Adam and mean squared error. Nothing actually new. And while fitting the model, as you can see, rather than just saying extrain and extrain, what we are going to do is we are going to input the excess are going to be extrain noisy. So the autoencoder is going to take the noisy images and predict the actual images. So we're going to take an extrain noisy and predict the extrain images. Right? And same for the tested too. We're going to take an X test noisy and predict the X test. Right? We're going to run it. Might take a little more time relative to the previous function. Yeah, pretty slow compared to the previous training thing, but still, pretty fast. I'm going to wait some time. Right? So yeah, it is converging pretty fastly, I think. But still, if like the loss might look like a magic number, but if you look at the training images, you feel like you could do a little more better. That is one thing while training like autoencoders. Yeah, so 70 block and it's already 0.007. So yeah, like it is decreasing like pretty fast, I believe. 0.0707 all that. As you can see here, there is no problem of overfitting. If you don't know about overfitting, then overfitting is a problem in which the model performs very better on like training set and performs very worse on training test set. You don't even encounter that problem. In fact, both of these training loss and validation loss are actually pretty similar. And in fact, if you look at the above examples, validation loss is actually much slower. Right? So it finished training. Right? Hopefully it finishes. Yeah. I mean, like, even the time it took, like, it just took like 15 seconds for like first epoch. And after that, it maintained a average of about 8 seconds per epoch. It's actually pretty good, right? So the training is finished, right? Now we can actually look at the summary of our model to actually see like the summary of the architecture. We have a conventional 2D layer with like a 14 by 14 by 16. The output shape is going to be 14 by 14 by 16, and then we're going to have 160 parameters, and we're going to have like another conventional 2D layer with like 7 by 700 by 8. So this is going to be like feature representation. Again, this is the encoder, and the parameters are like 1160. So therefore, there are like 1320 trainable parameters only in the encoder, right? We're going to have like 1320 parameters, weights that we have to update. And if for the decoder also, we're going to have like one convolution to transpose layer, whose output is going to be like 14 by 14 by 8. And the parameters are going to be 584. We're going to, in the next convolution to the transpose layer, we're going to have the output to be 28 by 28 by 16, right? And then the parameters are going to like 1168. And the final convolution layer will actually convert this output into the image 28 by 28 by 1, whose parameters are going to be like 145. So yeah, there are many parameters, 1320 plus 1900. Let's see how much that is. Yeah, approximately 3220 parameters to update. Not huge compared to the other models that we have done. So now we are going to do the same thing. We're going to take this noisy images that we have done above, pass it to the encoder, and take this encoder output and pass it to the decoder. And we're going to do the same plotting here, like to see how the images are there. Wow, like yeah, wow, okay. The performance is good. We have performed denoising. So taking this noise image, pretty noisy image, and we have converted like very smooth plain image, which is actually pretty good. Like if you look like there is like a lot of noise and the output is like pretty like clean. All right, now we have built the second application also, second thing, denoising. So yeah, we have also achieved like pretty good results, like very less training and very limited architecture. And we could actually there might be some disturbances here. You can look here, maybe there might be a little more different disturbances, but like the performance actually outstanding. Now let's build the anomaly detection. I'll download the data set from this link here, ecg.csv from TensorFlow, like this link, right? We could actually download that as a data frame, and we would use pd.read csv to actually download this data or read this data into our current directory, and we'd actually get the labels and the data. So data is actually going to be like I'm going to plot the data for you just here. I'm going to get the minimum value and maximum value of this training data, and we could actually like subtract the minimum value and divide by like the like outliers. So the range of this model, we'll do that, and we'll cache the data to be like floats. And then yeah, so this is the plotting data. This is the plot. This is the normal ECG, right? So this is like the normal ECG that you will have. For example, in any human, it seems that this should be the ECG, like this pattern. And this is like anomalous ECG. So from this data set, from this data, anomalous. So it is going to be like we are essentially going in the data set. We are going to have two classes, real and anomalous. So this is the anomalous ECG, and this the pattern does look kind of like not similar compared to this, and we want our model to actually predict that, right? Now let's build our model, the anomaly detector model. So what we're going to do is we're going to build a cell encoder, like similar encoder. We are not even using a convolution tree layer, because of course the data is numbers. We don't have to use any complex complex modeling. Maybe you could use like convolution 2D like one kernel, one by one kernel and all that, but there's no need. We'll be using a dense layer, right? So on this data, because it like time series data, right. And then we are going to have like one dense layer with 32 neurons and activation to be ReLU, and we're essentially going to convert this data in like eight dimensional feature vector, and we're going to use so this is going to be the encoder. We are going to encode this image into a very small feature representation, right? So this will be the output of the feature representation. And then now I'm going to build a decoder, which is going to take this input and perform like many more dense layers. And the final output is going to be 140. So we're essentially going to predict 140 points, or I think it's time. Is time? Yeah, probably time. Over time, the number of heartbeats maybe, or frequency maybe. All right, now we'll build the model. We'll just call it on. We'll take in the input image, pass that to the encoder, and pass that output of the encoder to the decoder. And we're just going to return the decoder. And we're also going to build the autoencoder. We'll get the object. I'm going to run that. Let's compile the model with Adam and MAE, mean average error, And then now, while training the model, again, we are not going to use the anomalous data in any kind. We are just going to train the model on real data, right? So that is the idea, right? I've shared the idea. We're essentially going to train the model only on real data, and we are going to make the make the autoencoder predict on anomalous data to actually see if it can replicate the anomalous data, the fake data, because the model is actually trained on real data. It could not be able to like reconstruct the fake data because of the simple fact that it is only trained on real data, right? It can only find features on real data, so therefore it can only reconstruct real data. So even if you give the song autoencoder anomalous data, it will not be actually able to reconstruct it. I'm going to run that. Hopefully it will be pretty fast. Yeah, pretty fast. 3 seconds. Imagine like 3 seconds for training a model. That to anomalous detector. Yeah, pretty good. Actually, plot this data, plot this loss function. As you can see here, the training loss converged and the validation loss stopped. I mean, this like I have said about overfitting, right? This could be a situation of overfitting, right? This could be a situation of overfitting. Now we could actually test this data on like this is first we're going to test this data we're going to test this model on real data. So this is the real data. This is the real data. And as you can see here, so this is the input. The blue lines are input, and the red lines is actually predicted our model, and the red colored area is the error. And we could actually set a threshold, right? We could set an error value, and if the error exceeds that amount, we could just say that the data is not real, right? And now let's do it on fake data. So this is the fake data, and as you can see here, the model is not actually able to reconstruct the fake data because it is not trained on that type of data. So that we could easily detect like how, like if a model is real or not. Like we could set a threshold to be some number of value, and we could actually, so this is the number of examples, and uh like yeah, so the a number of examples with the 0.05 loss is actually very higher. And then we could actually build this function to actually, yeah, take the calculate the accuracy, precision, recall, and you know, it works, right? Hopefully you got the idea of anomaly detection using autoencoder. So yeah, these are some applications of autoencoders. So thank you for watching, and I'll see you in the next video where we'll probably cover various autoencoders. So thank you for watching. See you in the next video.